People sometimes pretend they like to go back over these. So, good. What you wanted, that's not right. That's bad. What we wanted first up was the waveform, was it not?
Yeah.
Isn't that bad? V equals F lambda. I'm going to recalibrate this. So I'll just. Okay, so V equals F lambda. The next thing I asked you to do was
Acoustic impedance.
acoustic impedance. Almost.
I thought it was when you try to make sound less loud.
Well, it certainly has to do with sound because it's acoustic. We're doing ultrasound. So it's in this case to do with ultrasound waves and impedance. What would that word suggest? If you didn't know impedance, is there a word that sounds similar you might have heard of? Impede. So we can make a connection like we would in Super 6. If you're in the exam, you didn't quite know, you'd think impede. What does impede mean?
Stop.
Slow down, resist. So it's the way in which a material slows down or resists the passage of a sound wave. Rather than material, what's a better word? We talked about mediums for waves. Of the which, sorry? I don't, off the top of my head. Now, we said yesterday acoustic impedance in ultrasound technology is really important because you need some of the sound wave to pass through a medium and you need some to be reflected. If there's zero impedance, it would just completely pass through. If it was 100% impedance, it would completely reflect off, but you need some reflection and some passage. Okay, the next one I had was the formula, wasn't it? Okay, the formula for acoustic impedance, Z equals rho V. So it's the density of the material times the velocity the sound wave travels through it. That's simply a measure of how well the sound wave will go through that medium. Next one.
Whatever that word you said was, we're going to find another word for that word.
The word was sonde.
Yeah, I said ultrasound, but I have no idea.
There's a couple of words that can go with that. Probe, transducer. Yeah, can be a probe or a transducer. So it's actually the device which they use to give off the ultrasound and pick it up again. But it's a general term. So probes and transducers belong to anything which translates signals for use in a data processor. Z equals rho V, so it's acoustic impedance equals density times the velocity.
So that was Z.
That's Z is acoustic impedance. Yep. And the last word was?
Piezoelectric effect.
Piezoelectric effect.
Something that reduces electrical charge when it contracts and falls.
When it's compressed, yeah. Or they just say a crystal or material which produces a voltage when compressed. That's piezoelectric. Okay. Yep. This is a bit of a revision for you. It has got some extra details. We'll do this reasonably quickly and then we'll... Now, the first question you always ask yourself when you look at something like this, guys, is very simply, is there a reason that I should not trust this particular piece of information. When I found this, they're not real people. This actually comes from a medical imaging course at a university. So these people are doctors and they're people who lecture in this. So I mentioned yesterday that the Curies were the people who discovered the piezoelectric effect in the 1880s, and they discovered it with quartz. When they say the Curies, it was Marie and her brother. I think his name's Pierre of all things. It's a bit... Okay. Marie was involved in it somewhere. And then you have the fact that it was actually used in the 1940s for sonar. And the first medical applications came in the 1950s. Now, one thing that I find interesting as a geophysicist is a lot of the techniques I used to see in geophysics have now been adapted into medical imaging. So the geophysicists might have been using these things for 10, 15, 20 years, and then medical physics come along and use them. Ultrasound, they define as sound waves greater than 20,000 hertz. Again, that is not a well-defined number. It changes depending on the source you look at. But I was just a generic person. The reason they use 20,000 is essentially that's the upper limit for what people hear naturally. And don't forget, whales and things we saw get up to 150,000 hertz. So it's not that animals can't hear those sounds, it's that humans can't. And that's how we define things. So we use diagnostic medical ultrasound is using high frequency sound to look at the diagnosis and therapeutic treatment of people, not students, of people. So it can be both diagnostic, it can be therapeutic. Our course is concerned with the diagnostic side of it, not the therapeutic. And the intensity of the ultrasounds and the frequency depends upon the use. So you can see that they talk here about 2 to 15 megahertz is the range for ultrasound usage. It uses the piezoelectric effect, which means that by applying pressure to or compressing a crystal, you can produce a current from it. Equally, the reverse piezoelectric effect is when you apply current to a crystal, it causes it to compress. And so if you apply high frequency AC to a piezoelectric crystal, it will cause it to vibrate, just like a Kona speaker, making connections with 2LS, and that will produce the sound wave that we're after. So in this case, the piezoelectric effect involves a transducer, and a transducer is simply a device which converts any form of energy to another form of energy. A speaker is a transducer. The sonde is actually a device which is used to detect or send out signals for information. So, a speaker converts electricity into sound. What does a piezoelectric crystal do? Converts electricity into sound. Now, what we do is send pulses of sound to the soft tissues, and you get interaction with this. You can get sound interaction with the soft tissue called bioeffects. But the thing that we're looking for is passing the sound waves through the interfaces and getting some reflection and some transmission. And the strength of that reflection and the time it takes to get from the transducer to that boundary and back allows us to make an image of it. Now, the way that the sound wave passes through it will vary according to the medium, so that, as we know, fluids will allow travel, the sound wave travel faster through it than will gases, and very dense solids allow them to go faster again. But the density has a relationship to the velocity. Shadowing is okay. It's a bit like seismic in geology. What happens is you get interference effects going on from reflected waves. Because don't forget, if you have two boundaries, the wave can pass through the first boundary, hit the second boundary, and then it goes back to that first boundary again. When it hits that first boundary, 100% of it's not going to go through, is it? So some of that will reflect back again. And you get these trapped sound waves that bounce back and forth between the layers, and they will eventually, some of that energy will be released at different times. You end up with interference effects in your imaging, and so it's not totally clear. What you need to look for are very strong boundaries to pick up and make your images. That's why when you look at muscle, which I'll show you in a moment in an ultrasound, it looks quite dappled because of the interference effects in it. Now, so you get these echoes by soft tissue, and the good thing is that the soft tissue does produce enough echo for the transducer to pick it up and make the image that we're after. We know about frequency, I don't need to talk about that. And that talks about types. 1 cycle per second is a hertz, 1,000 is a kilohertz, 1,000,000 is a megahertz. So 7.5 megahertz transducer means 7,500,000 cycles per second. So that's moving quite well. We know about wavelength, and we know there's a relationship between the wavelength and the frequency from the wave formula. What we didn't do yesterday is we didn't go through the fact that different types of frequencies are used for different types of diagnostic investigation. We did note that changing the frequency did change the depth at which it would penetrate. And so 2.5 megahertz is used for obstetrics and gynecological work and for deep abdomen. General is abdomen, and obstetrics to gynecology is 3.5. 5 megahertz can be breast, vascular and gynecological and so on. You don't need to reproduce those for this course. Doesn't hurt to know them. Now, we did talk about attenuation. Attenuation is a reduction in the sound intensity as it travels through tissue. You lose sound energy. Now, we know that higher frequencies attenuate or absorb faster than lower frequencies, but also you need higher frequencies to get greater depth of penetration. So you've got this double-sided thing. You need the frequency to be right to go through the body, the depth you need, but as you increase the frequency, you get better resolutions and other things going on. You also increase attenuation. You don't need about time gain compensation. Resolution is the ability to see more detail. So the higher the resolution, the more ability you have to see detail and things. That's important in this sort of stuff that you're looking at. Now, notice, as the frequency goes up, the resolution improves, but what goes down as you increase the frequency? The amount of energy that returns, because as the higher frequency goes up, attenuation increases. So you're always playing this game between the right frequency and trying not to have too much attenuation, but at the same time getting good resolution. And you can see here the same image at 3.5 megahertz and at 7.5 megahertz. And you can see the difference in the resolution of those pictures. And there is this, something that's not mentioned in the syllabus is dynamic range, so we don't need to worry about that too much. So higher frequency is improved resolution, you get depth of penetration changes, and you get more loss through attenuation. But with low frequency, you get poorer resolution, you get a better depth of field, but you end up with also less attenuation. Now, the actual machine is made of a transducer, which has the various crystals aligned, piezoelectric crystals. So what happens normally is the first one will be pulsed, then the second, then the third, and what happens is the first one will send its pulse down, it gets switched off, and when the sound wave comes back, that signal is processed. By then, one of these is firing. So they pulse it in turn through the crystals. So the crystal becomes a sound source, and then a little bit later it becomes the detector. Okay?
The crystals actually in
The head, the transducer they put on you. Yeah. The sonde, yeah. Hmm? 6. Yeah.
If you have more crystals
Yes, yes. So you can get these with just a small arrays, or you can get large arrays, the linear and the sector. And there's various modes for looking at things. There's the B mode, which is the grayscale. You've got the B mode colour, got an M mode, and you've got the Doppler mode going. And they have pictures of these, and these are available for you to see. So you can see the Doppler effect ones, which pick up the flow, which we talked about yesterday. This duplex and triplex means that not only do you have the picture, but you've also got graphs which show what's going on with the flow of materials through the body.
Duplex is actually moving two ways.
What it is a split screen image. So they've got it's referring to the amount of information on the screen, the way it's monitored. So you can see you've got a graph, which is the flow of blood shown graphically, and the flow of blood shown in the Doppler ultrasound image.
So what's in the, which one's the duplex, which one's the drive?
I suspect, not being a medical technician, I'm getting a medical technician in to talk to you in a couple of weeks' time to actually go through it. I suspect that's duplex and that's triplex. I wish I could, but I don't know any. Is he?
Yeah. He's got a PhD in it.
Okay.
Jack, go on, looking back to you.
What?
Go on, looking back to you.
Okay. Very quickly, very quickly,